All right. Hello, everyone. Don't see a timer, but OK. Hello, everyone. My name is Sanchit Sabhlok. I am a fifth-year grad student here at UCSD. Work with Professor Shelley Wright. Some of my other collaborators are listed here. All grad students and Sonatas in the first row here. And I'll be talking about proto group members around distant radial out quasars. When I say distant, it's about redshift of 2. And if you take nothing else from this talk, these are the two images I want you to take away. These are beautiful Ly-alpha nebulae around these quasars, and the quasars at the center of the big red region there. All right, so why are we doing this? Let's start with the biggest picture of them all, the large-scale structure. So lambda CDM paradigm, it tells us how the universe is built up. It tells us that small structures assemble first, and they assemble into these larger structures, eventually forming what we now see as the cosmic web. Forming these massive clusters around these galaxies and these cosmic filaments that you can see. These overdensities start to emerge as around redshift of 6, and you can kind of see them. But right around redshift 2, some of these structures start to materialize, and you can hopefully view some of these filaments. So we want to study how these structures evolve. And to do that, we kind of need to know how these galaxies evolve as themselves and what is their environment around them. So the circumgalactic medium around a galaxy plays an important role in building them. So we've seen this figure if you've been around this topic before. But this medium, it's diffuse, it's multi-phase. It has got these cold, warm, hot components. It's clumpy. And it's critical to a galaxy's evolution because it fuels the star formation. And of course, also is a recipient for potential outflows. So we expect it to be metal rich in nature. But what we would like to do is observe it in a galaxy and actually study this, because historically this has been hard to do. But now with KCWI, MUSE, these instruments coming online, you can actually study the nebula around these galaxies. So what we would like to do is observe this assembly. So what the period I'm looking at is redshift 2, which is also known as the cosmic noon. So we've seen the plot that the star formation rate and AGN activity have peaked around this time. But we also see, if we try to look at what clusters have we found and what protoclusters have we found, we find a lot of clusters for up to redshift of 1. And going beyond that, we find some high Z clusters. And beyond that, we start seeing these protoclusters at high redshifts. But right around here, there's this period of transition. So what I would like to do is look at some of these specific individual cases. And make a detailed study of the kinematics around these gases. Why is there emission? What's causing it? So these are likely progenitors of massive clusters we see today, and we would like to study these in detail. How do we find and study them? So radial loud quasars have been shown to reside in these regions of overdensities. So this is the Village-Alec paper I'm quoting here. So we would like to use these as these cosmic lighthouses, which guide us to these structures potentially. So we have a sample of 14 high redshift quasars known as Quart. And we had originally made the sample with these extremely high radial luminosities. And we targeted these with Keck AO. And now we wanted to check, OK, do any of these quasars reside in these regions of overdensities? So we first targeted these with KCWI to map the Ly-alpha and He-II emission around these sources. And then what we did was we performed an overdensity analysis of the larger fields around these quasars. And we used Spitzer data for this. We used Hubble with C3 and Subaru hypersupreme CAM data. And we identified overdensities around 2 of our sources, 3C9 and 05.84. And these are the sources I'll be presenting today. So we went fishing. We looked for proto group and proto cluster members around these quasars. And we looked around the much larger field, but also in the immediate vicinity of the quasar. So what do I mean by that? So this is the Spitzer field for 3C9. My quasar's in the center. And I have these 1 and 2 arc-minute radii around this. And if we do a color cut to select high redshift sources using Spitzer IRAG data, we find there's about a 3.5 sigma overdensity of sources at redshift greater than 1.4. So what we wanted to do was target this larger field. We did this using MOSFIRE, but if you see this here, I've outlined the KCWI field of view, and we also wanted to look for potential members very close to the quasar. So we had a 2-pronged approach here, and these are the masks we used with KCWI, MOSFIRE. So first, let me show you the KCWI image, and that's the image on the title, and why we chose some slits in the immediate vicinity of the quasar. So these are the images here. I'll show a few of these, and they'll all have the same units. So this is the surface brightness map in flux units here, and these are the velocity and dispersion maps around this quasar. So first of all, we see this beautiful Lyman alpha, about 100 kiloparsec structure around this quasar, and we see that it has got these clumps of high brightness. And if we look at the radial velocity distribution around this, we see there's this extremely high velocity complex south here, and it also shows incredibly high dispersion around this region. So this is the region we targeted with MOSFIRE, but if you look at this plot here, the contours that I'm showing are regions where we also detect helium-2 emission. So these are the plots for that. As you can see here, again, it shows surface brightness variation across, but it is also a region of extremely high velocity difference. And all these velocity differences have been calculated with respect to the systemic redshift of the quasar. So this is this huge complex with not a lot of dispersion, but with incredibly high radial velocity with respect to the quasar here. And so we went and looked around this using MOSFIRE. So these are the slits that I'm showing here. And the colors correspond to the corresponding 1D spectra that we've extracted. So this slit here, for example, shows this spectra, which was along that complex of high dispersion. And you see this beautiful source here. In fact, you can see the quasar continuum right at the top of the slit here. And we find 5 of these sources around the quasar, and we think we've done a good job. We found a source there. There's probably star formation activity, except we find that the velocity difference with respect to the quasar is about 3,000 kilometers per second. The good thing is we find this one source here, which actually aligns with the velocity difference we see for the CGM. So it is likely embedded in the CGM. But these other sources are redshift from the redshift of the quasar, and we want to study what are the kinematics that are causing this in the future. We did this for another quasar, which shows an even greater 8 sigma overdensity of sources. And we did the same procedure. This image is now from Subaru Hyper Supreme Cam. And we had 2 masks for this for MOSFIRE. And we again detect an extended Lyman alpha emission, but now this nebula does not have the extreme radial velocities that we saw with the other quasar. In fact, we see this region here, which is exactly at the redshift of the quasar. And that is where we see peak helium emission for this quasar here, which is this contour outline here. And it does not have the velocity gradient that we saw in the other quasars. Something drastically different is happening in this system. Again, we targeted this with MOSFIRE to see what's going on in these regions. And while we detect oxygen lines in the spectrum, they seem to be closer and well aligned with the CGM emission that we have detected so far. And so we think these are in fact embedded within the CGM that we see with Lyman alpha and helium-2. So the big point I would like to drive home here is first, we have detected these nebula, but even though these are radial out quasars, they're similarly sized nebula, they seem to show different kinematics for the sources we have detected with MOSFIRE. And we detect 5 of these sources around 3C9, 3 around C05.84, and it shows the importance of going and looking at these individual cases and trying to study the sources with different wavelengths, trying to see where the emission's coming from, so we can better understand these proto-group environment at these critical redshifts. Lastly, we spatially correlated these group galaxies with Lyman alpha and helium emission, and we find at least 1 source is directly embedded in the CGM for 3C9 and 2 for C05.84 based on these radial velocity measurements. So that's a slide, and I can take questions now. Thank you.
All right, any questions in the room? So you have the CWI spectra of these things, and a couple of these things have pretty high velocity dispersion. Do you see anything in absorption in these CWI spectra that gives an implication?
So one thing I did point out, and I should have, oh, sorry, I'll repeat the question. The question is, we had the KCWI spectra for these quasars. Do we see anything in absorption for these spectra? So the plots that I showed you for both of these have been PSF subtracted from the quasar. So we've taken the PSF out. This was developed by Andre Weiner, who's at Johns Hopkins now. This entire nebula that we're looking at, if you look at the Lyman alpha, it's a narrow single peak. So the absorption you'd expect in the quasar spectrum itself and in that sight line, so that's there, but this is looking purely at the CGM around the quasar. So we don't have any absorption in these lines because we're not looking at the quasar emission here.
Perhaps I'll clarify. For the candidate other things in the proto, whether or not there are absorption features in the KCWI spectrum that are coincident in redshift with.
Okay. So in the quasar spectrum, do you see the site? Okay. Yeah. So to clarify, the proto group members that we see with these velocity redshifts, do we see them in the quasar spectrum? So we do see absorption in the quasar spectrum, but I haven't correlated it with any of these sources just yet. It's possible it could be coming through the sight line, but we still need to look into that. I'm not sure where that absorption is coming from, but it could be from the sources. Just not sure yet. All right, please read it. Have you estimated the gas mass associated with the nebula? Do you know whether or not it is possible for the QSO to heat up all that gas? So we have not, that is one of our next steps to estimate the total gas mass around this based on these group members that we have found. We believe it is possible for the quasar to light up this helium complex immediately south of the quasar that we detect for both these sources. The fact that we detect oxygen 3 and H alpha mean there could be potential star forming activity. There could be a smaller quasar that's also illuminating these regions. But it's certainly possible, although we can't confirm that just yet. There are several possibilities.
All right, any other questions in the room? All right, one more big hand.